today we are going to be talking about depth first search in directed graphs. In the last class we have looked at, in the last two classes we have looked at depth first search in undirected graphs and seen applications of the same. So, how does depth first search in directed graphs differ from depth first search in undirected graphs, right. So, let us take an example of a directed graph. Let me make sure this has something interesting happening. Okay, let us put this edge back here. So, suppose this is the directed graph that I start with, okay, and this is my start vertex. So, the process is going to be exactly the same. Okay. So, as in the depth first search, so the code for depth first search would remain the same. Let me write it down once again for your benefit. So, depth first search from a vertex v, what did we do? We set visited v to 1 and then for all w adjacent to v, what do you do? If not visited w, then DFS w, and this was the code for depth first search in undirected graphs. Now, this is the same code for depth first search in directed graphs. I just need to redefine what adjacent means now. What do you think adjacent means? Right. So, a vertex w will be called adjacent to vertex v if I can go from v to w. Yeah. So, I am at vertex v, I want to look at all the vertices to which I can reach from v, right. So, these three vertices would be adjacent to v. So, sometimes the term out adjacent is used, because you might also want to call this vertex adjacent. So, x will be called in adjacent. Okay. But when here we talk of adjacent, we mean out adjacent vertices to which you can go from vertex v, okay, and the rest is the same. So, let us see what will happen now. Let us say I start from this vertex S and I took this as the first edge to go out. I came to this vertex. Now, I took this as the first edge to go out. So, I came to this vertex. Now, I will consider the edges going out of this vertex. How many edges are going out of this vertex? Only one, which is going to a vertex which is already visited. Yes. So, there is nothing more to be done at this vertex. I will backtrack from this vertex, go back to where I came from. I came back, come back to there. Now, here from here I am going to look at the other edges which are going out of this vertex. There is one more edge. So, that will bring me to this vertex. From here I am going to look at the edges going out of this vertex. There is only one edge which is going out of this vertex, that is going to bring me to this vertex. From here I am going to look at the edges going out of this vertex. There is only one edge going out of this vertex which is going to a vertex which is already visited. So, I am done here. I backtrack, come back here, yes, backtrack. Okay, why do I backtrack from here? Because there is no other vertex edge going out of this vertex. So, I backtrack, I come back here. There is no other edge going out of this vertex. So, I backtrack, I come here, yeah, and from here now I will, what will I do? I will look at the other edge going out, this is going to this vertex. So, I come to this vertex along this edge, okay, and from this vertex I look at the other edge going out, any edges going out, there is this edge going out, but it is going to a vertex which is already visited, yes. So, I backtrack from this vertex and I come back to here, there is no other edge going out of this vertex. So, I backtrack from S, which effectively means I have finished the procedure. Okay. So, this is what DFS here would look like. Let me give the arrival and departure numbers to these vertices, so that it is completely clear what we are doing. So, this 0 Can someone quickly tell me what these numbers would be? 1 here, 2, 3, 4, 5, 6, 7. That's very easy, right? You're just saying 1, 2, 3, 4. You're not putting it down on the paper. It's harder for me. 7, 8, 9 here, 10 also here, 11 here. Okay? It's clear? So, this is how our depth first search happens. Okay. Now, suppose let me modify this graph a bit. Let me change the direction of this edge. Let me make it this way. What will happen now? This vertex will not get visited. Yeah. So, what will be the departure time of this vertex now? So, we will come back to this vertex. So, I departed from here at time 8, I came back here, come to here, and now there is no other edge going out. So, I will finish at time 9. Now, what happens? What about this vertex? When will this get visited? Right. Now, we are going to, so depth first search, when it starts from a vertex, might not visit all the vertices. This is true even in the case of undirected graphs. It will not visit all vertices if the graph is not connected, for instance, right, as was the case of breadth first search. You started the breadth first search from a vertex, it would visit only the vertices in that connected component. Similarly, depth first search in an undirected graph would visit only the vertices in that connected component. In a directed graph, the depth first search would visit only such vertices which can be reached from this vertex, such that there is a path from this vertex to that vertex. उन्हीं vertices को हम visit करेंगे. There is no path from this vertex to this vertex. Why? Because this vertex has no edge coming into it now. There are only 2 edges going out of this vertex and no other edge coming in. So, there is no way of going from here to here. In fact, there is no way of going from any vertex to this vertex. Right? So, this vertex does not get visited when we do our first depth first search. But just as in the case of breadth first search, what we did was, if some vertices were not visited, we took a vertex which was not visited and started our breadth first search from that vertex. So, similarly, we are going to do that here. If some vertex is not visited after we finish our depth first search from this vertex, then we are going to pick that vertex which is not visited and continue our depth first search from there, right. So, which means that I am now going to pick this vertex, give it an arrival time of a 10 now, look at the edges which are going out of this vertex, they are all going to vertices which are already visited. So, there is nothing to be done. So, which means that I also finish this depth first search. In this manner, every vertex is going to get both an arrival and a departure time. Yeah? Okay. So, I will keep this picture and I will again redraw the tree, right, the depth first search tree. We did a similar thing the last time. We have to visit all the vertices, right. So, both breadth first search and depth first search require that you go visit every vertex. So, while I did not elaborate on this when we were discussing depth first search in undirected graphs, but there I was assuming the graph was connected, right. So, if the graph is not connected, you did a depth first search from a vertex, you visited a bunch of vertices. If you have not visited all vertices, then you will take another vertex which is not visited and start your depth first search from here.
To see that whether this vertex has not been visited, we also have to go through once again through all the vertices.
So, we had looked at a procedure for doing this in a clever manner when we were looking at connected components, right. All we have to do is traverse the visited array to find the first vertex which has still at a 0, and we will never have to retrace. We will just have to make one scan of that array, right. We can adopt the same procedure here. Okay, so let me now draw right. So, these are the tree edges that I have drawn. Now, I am going to draw the back edges. Okay. Okay, now we will understand what kinds of edges can there be. Just one second. I have drawn all the edges, as you can see. So, the tree edges are in blue, right? Pardon? Huh? You can't see the colors. Wow. I didn't realize that. That's tragic. Let me try to make them darker. Can you see the color now? It looks a deeper black, huh? Okay, fine. Okay, so yeah, so good that you pointed out. Is it only today that you can't?
Every time your pen moves on that, we assume that it is the same color.
Is it better? Slightly.
But because you use that pen, now we're realizing it's blue.
So this blue edge, yeah? No, it's not blue. Okay. Does it look blue now? It's red.
So we have to make that out by using the sketch pen that you are using.
Right. चलिए कोई बात नहीं. Hopefully the others who are watching this program will be as smart as you are. Huh? 1,8, 2,3, 4,7, 5,6 and 10,11. Okay. Now, we do not have the nice picture we had in the case of undirected graphs, that all edges are in two categories, either tree edges or back edges. As you can see, there are 3 different colors already, and I have not yet used a 4th color. There is also a possibility of a 4th color, and let me show. You could also have an edge which goes from here to here. This is green clearly, right? This edge could have been there. Why? Suppose this edge was there. Yeah, I am continuing to follow this path. When I come back here to this vertex, I look at the other edges going out. This is another edge going out, but its other endpoint is visited, right. So, now we have to classify these edges, we have to give them names, right. So, our green edge, this edge is a forward edge. Why forward? Because it is going forward in the tree, right, down. We will call that forward. The brown edge is a back edge, it is going back up in the tree. We do not use the term backward edge, we just use back edge. Yeah, there is nothing backward about the edge. The red edge is called a cross edge.
Which one is brown? So which is red? The point.
This is a red edge, and this is also a red edge, and this is also a red edge. These 3 are red edges. The black also, the brown also looks like black, is it?
Looks like red.
The brown edge is that edge, it is a back edge, right. So, it should be clear, tree edge is completely clear, right. An edge along which we traverse is called a tree edge. Okay. Now, something that is going forward in the tree is called a forward edge, something that is going back in the tree is called a back edge, something that is not going either forward or back is called a cross edge. So, what is the property of a cross edge? Not going to ancestors or to a descendant. right. The two endpoints of the edge do not have an ancestor descendant relationship, not parent child, ancestor descendant relationship. The two endpoints of this edge are, none of them is an ancestor of the other. Similarly for this edge, none of them is an ancestor of the other. Right? This is one tree, this is another tree, so to say, just a singleton vertex. This is not an ancestor of any of these vertices, right. So, these three are cross edges. Could I have a cross edge which goes in this direction? Huh? It would have become a tree edge. So, cross edges go in one direction only. What is that direction? Huh? Okay, so we will translate all of these into numbers very soon. But essentially, if you draw a picture in which you are first visiting the left side of your tree and then going right, then they are going from right to left. The cross edges only go from right to left, so to say. Not higher to lower, but more like right to left. Right? This cross edge is also going from right to left. This is also going from right to left. We'll this is a bit subjective, but I'll tell you what the actual thing is. Okay. So, what is the property of a forward edge? Who can tell me? So, what is it that makes an edge a forward edge? Right. So, a forward edge, for a forward edge, how can I relate its arrival and departure times? So, if I have an edge uv which is a forward edge, what can I say about the arrival of u versus the arrival of v? Pardon? Arrival of u? It is a forward edge, such an edge. So, this is u, this is v. So, I would have first reached u and then I would have reached v. What can I say about the departure of u versus the departure of v? Clearly, I will leave this before I leave that. So, departure of v is less than the departure of u. That is for a forward edge. I can play the same game. Let me now say it for a back edge. Once again, I have a uv back edge, right. So, arrival of u versus arrival of v, which is smaller? This is a back edge, this is u, this is v. V will be smaller, because when I am saying the edge is uv, in a directed edge I always specify the tail first. This is u, that is v. This is v, then I reached this before I reach this. So, arrival of v is less than the arrival of u. What about departure? Departure of u versus departure of v. Departure of u, it is a uv edge, I will leave u before I leave v. Now, let us come finally to our cross edges, and since this is more important and you have not seen this before, once again uv is a cross edge. If this is a cross edge, this is u, this is v. What about arrival of u versus departure of u? Arrival of u versus arrival of v. This is u, this is v. Arrival of u is greater. If this is u, this is v, I will reach here after I have reached here. Arrival of u is greater than the arrival of v, right. So, I will first arrive at u, actually then I will depart from u, yes. So, I should actually write it in a more sophisticated way as departure of u, sorry, arrival of u is not greater, I first less. I first arrive at u, then I depart from u, then I arrive, oops, what am I saying, sorry, I have managed to create a mess there. Let me do it again. So, we are considering a cross edge. Can you all see this picture? Let me consider a cross edge again. I am looking at an edge uv, right. So, in my picture this is u, this is v, now it should be clear, right. So, which vertex will I reach first? V. So, first I reach V, then I leave V, that is important. Then I reach U, then I depart from U. Yes? Okay. So, the arrival and departures are arranged in this way for a cross edge. Okay. Great. So, in a depth first search, the edges get classified into 4 categories, right, and based on the arrival and departures you can figure out what those categories are, right, or based on the fact that whether they are a tree edge or not. So, first you will create the tree edges, first you will identify what the tree edges are. Using the tree edges you can identify parent child relationships, also ancestor descendant relationships, and using that you can figure out whether it is a forward edge, a back edge or a cross edge. If the 2 endpoints have a ancestor descendant relationship, then it is either a forward edge or a cross edge or a tree edge. If they do not have, then it has to be a cross edge. Sorry, in the first case it is either a forward, a back or a tree, in the second case it is either cross edge, right. And when you have to distinguish whether it is a forward or a tree or a cross, then again if it is based on whether the ancestor, whether the tail is an ancestor of the head or whether the tail is a descendant of the head. So, you can use that to figure out these things. Okay. So, as an application we are going to look at how to check if a given graph has a cycle or not. So, that is the application we are going to look at. So, I am giving you a graph G. So, given a directed graph G, check if G has a cycle, right. What is a cycle in a directed graph? So, it is basically a path which closes on itself, right. The starting and the ending of the path are the same. So, how will you check if a given directed graph has a cycle? How will you check if a given undirected graph has a cycle? Huh?
If we have any baggage.
If we access the starting node without backtracking.
DFS कर दें अगर हम, ठीक है, and अगर कोई backage आती है, so then there is a cycle. If there is a backage, there is a cycle. If there is no backage, is there no cycle in the graph? Because then the remaining edges are just tree edges, they form a tree. A tree does not have a cycle in it, right. And a backage, why does it form a cycle? Because the 2 endpoints of the backage are connected in the tree, right. There is a path between those 2 endpoints. So, for a undirected graph it is very simple, for a directed graph it is not so simple. When does a directed graph have a cycle? So, once again you want to do a depth first search. In a depth first search, in what, if there is a backage, then the graph has a cycle. If we encounter a backage, then G has a cycle. Great. Why? Well, let us just look at an example. This was the tree, this was the backage, What is the cycle? Well, the cycle is exactly this. Since it is a tree, this node is an ancestor, this is a back edge. So, this is an ancestor of this. If this is an ancestor of this, there is a path in the tree from here to here, right. I will go down to its child, one of its child, and then so on and reach here, and this together with this forms the cycle for us, right. So, if there is a back edge, there is a cycle. If there is a cross edge, does that mean that there is a cycle? So, question is, if there is no back edge, does that mean G is acyclic? I am using a term here. What does acyclic mean? No cycle.
Consider a cycle itself, that will consider a graph which is only a cycle, then definitely will not have a back edge.
He is saying consider a graph which is only a cycle, we will not have a back edge. It will have a back edge. Is that clear? So, he is saying consider a graph which is only a cycle. इसका depth first search क्या होगा? When we do a depth first search of this graph, what do we get? No matter what vertex I start from, I will, let us say, go down here, then I go down here, then I go down here, here, and at this point this will become a back edge, because I will just retrace my path here and reach here. So, this will become a back edge, right. So, back edge, if you find a back edge, there is a cycle. If there is a cycle, it seems that you will get a back edge. Can we prove this? If there is no back edge, does that mean that there is no cycle in the graph? No. If there is no back edge, does that mean G is acyclic?
Due to a cross edge also, because it can happen that in a particular cycle the child is traversed by some other path, like the origin of cross edges. So I'm just
so सब कुछ लगता है, फॉरवर्ड एज भी साइकिल बनानी चाहिए, क्रॉस एज से भी साइकिल होनी चाहिए, क्रॉस एज Okay, so let me do a very interesting proof of this statement. Or what is the statement? Oh, this is not a statement, this is a question, right. So, the statement is no back edge means no cycle. No back edge no cycle.
For the cycle, sir, does that mean arrows going on only one direction?
Of course, this is a directed graph, right. A cycle means a path, and it is very clearly specified in a directed graph. A path means you can go from one vertex to the next. Think of them as one way streets, right. So, a cycle would mean only if you can traverse in such a manner such that you can reach the starting point. Great. So, no back edge means no cycle, and how am I going to prove this? Let me do the following. I will do a depth first search, yeah, and now I will order the vertices according to their departure times. So, do DFS, order vertices by their departure times. What does that mean? Let us say I will first put down the vertex which has the largest departure time. से smallest करना चाहते हैं, चलिए smallest कर लीजिए. हाँ, क्या करना चाहते हैं? Smallest. Okay, चलिए, this has the largest and this has the smallest, and the departure times are decreasing like this. This is the largest. ठीक है. अब और यहाँ पे हमारी, so this is the vertex which has the largest departure time. No two vertices have the same departure time. Yes, because every time we depart from a vertex, we change the time. So this is the vertex with the next smallest, the next smallest, the next smallest, and so on and on. Yeah. Now, let us go back to all that we have done so far. Let us look at this picture. For a forward edge, if u v is a forward edge, then the departure time of u is more than the departure time of v. Okay? Yes. So, the departure time, if u v is a forward edge, then the departure time of the u is the tail, v is the head of the edge. The edge is going from u to v. The departure time of u will be more than the departure time of v. So, if I have a forward edge, then will it go from left to right or will it go from right to left? If I have a forward edge, its tail would have a higher departure time. So, it would go from left to right. A forward edge would look like this. Okay? Okay. Let us look at a cross edge now. A cross edge, UV cross edge, the departure time of u is again more than the departure time of v. So, the edge will also go, a cross edge would also go from left to right. अब कौन सी एज बची? फॉरवर्ड एज तो है ही नहीं. अगर फॉरवर्ड एज होगी तो साइकिल है ग्राफ में. सॉरी, फॉरवर्ड, सो फॉरवर्ड हो गई और क्रॉस हो गई. बैक एज होगी तो देयर इज अ साइकिल इन द ग्राफ. सो व्हाट एज रिमेन्स? ट्री एज. What is the property of the departure time? If uv is a tree edge, then departure of uv, u ऊपर है, v नीचे है. So, first I will leave from v and then I will leave from u. So, departure of u would be more than the departure of v. Great. So, a tree edge also goes like this. Okay? All edges are going from left to right. How can there be a cycle? Can you create a cycle by just going from left to right? No. If you have to come back to the starting vertex, अगर आप यहाँ से शुरू हुए and you have to come back to this vertex, so you can go forward, but at some point you have to come back. But there is no edge which is coming from right to left. So, there is no cycle in this graph. ठीक है? Yeah, everyone follows this proof. Now, you know why we were worrying about departure times. Huh? So, you have to do this with departure times. You can't do this with arrival times, unfortunately. So, try that as an exercise. If I were to order them by arrival times, this is not going to work. Okay? So, this is actually a very simply proved theorem. If there is no back edge in the graph, then there is no cycle. If there is a back edge, then there is a cycle. So, all you have to do is do a DFS. If at any point you encounter a back edge, you declare that the graph has a cycle. If you are able to finish your depth first search without encountering a single back edge, then you declare the graph is acyclic. Okay? What is an acyclic graph? An acyclic graph is a graph which does not have a cycle. Yeah? And this ordering, so what we have, another thing we have shown, and that is a very nice thing, is that given an acyclic graph, let us say G is an acyclic graph, we can order the vertices of G so that every edge goes from left to right. Yes. That is what we did here. We said we started with an acyclic graph. We started with a graph. We did a depth first search on the graph. We did not encounter any back edge. So, we said the graph does not have a cycle, it is an acyclic graph. And then we said let us order the vertices of this graph according to decreasing departure times. Then what we see, if we order the vertices in this manner, then every edge goes from left to right. Okay? This ordering is also called a topological sort. Okay. So, in an acyclic graph, you can order the vertices, linearly order the vertices, so that the edges are going only from left to right. This ordering is called a topological sort. So, how much time do you take to find a topological sort? You just have to do a DFS and then sorting. Check what? हाँ, तो package तो ठीक है, but you have to produce an ordering of the vertices, right? So departure times के हिसाब से आपको right. So we don't need to sort because we know what the departure times are. What is the maximum departure time we can have? 2n. Yes? 2n, actually 2n minus 1, because each vertex is getting 2 numbers, right. So, the total set of numbers that we are going to be assigning arrival and departure times will be in the range 0 through 2n minus 1, right. So, the departure times are at most 2n minus 1, that is at least 1. So, I can just have an array with 2n entries in it, right, and as I depart from a vertex, as I assign it a departure time, at that position in the array I put down the vertex. I just need to make one scan of this array to get the vertices in the right order. Yeah. So, you do not need to sort the departure times, because if you had to sort, you would take n log n time, right. We have not seen a sorting algorithm which performs better than n log n. Okay. So, this ordering is called a topological sort and it can be computed in order n time, order m plus m time. Right. So, I have used, so I should also tell you about another term that is used for an acyclic graph. So, we are talking of directed graphs here, right. A directed acyclic graph, a directed graph which is acyclic is also called a DAG, D-A-G. ठीक है, right. These graphs arise quite a bit in circuits, right, in combinational circuits where your pulses are essentially traveling from one side to the other. There is no notion of a cycle, there is no loops, right, and so these graphs model that, and we can do a lot of things on such kind of graphs which we cannot do on a regular directed graph, a graph which has cycles in it, right, and we will see some of that in this course. Questions so far? नहीं? ठीक है. So, let me introduce, I will like to take one more application of directed of DFS in directed graphs, and since that is a longer application we will not be able to finish it in this class, but I will develop the terminology for it. Okay. So, let us go back to our notion of, so for undirected graphs, so if I gave you an undirected graph, there was the notion of whether the graph is connected. Yeah. When is an undirected graph connected? When all its vertices. There is a path between every two vertices, right? Then we say that the graph is connected. So, connected means there is a path between every pair of vertices. Okay. In a directed graph, the corresponding term is what is called strongly connected. Okay. A directed graph is called strongly connected if there is a path between every ordered pair of vertices. Why am I using this term ordered pair of vertices? Right, between which, so I said pair of vertices, but it is a directed graph. Maybe there is a path from u to v, but there is no path from v to u, right. Let us take an example. Is this graph strongly connected? Let me label. Right. There is a path between A and B, but there is no path from B to A. There is a path from B to C, but there is no path from C to B. There is a path from D to C, but there is no path from C to D. मतलब ये मैंने कुछ ज़्यादा ही ख़राब बना दिया ग्राफ. ओके, अगर हम ये भी कर दें, it is still not strongly connected. There is a path from A to B, but from B to A there is no path. Still. Pardon? Yeah, sorry. No. When I say there is a path from A to B, it basically means that I can go from A to B like this or like this. Right? But I cannot go from B to A. There is no path from B to A. Okay, is there a pair of vertices which such that there is a path between those two vertices in both directions? No, it cannot happen, right? Because not in this graph. Okay, let us see more examples which will perhaps be better. Okay, so A, B, C, D. Is this strongly connected? No? Yeah, between any two vertices. So, from D to B there is a path, from B to D also there is a path, because everything is on a cycle. Yes. So, this graph is strongly connected. Is this graph strongly connected? A और F के बीच में path है? Is there a path? Sorry, is there a path from A to F? Yes. A and F. There is also a path from F to A, going like this. So, this graph is also strongly connected. No, okay, that is not sufficient, right? You can't just take two pairs and check them and say it is strongly connected. You have to look at every pair, right? But you can check. देखिए, all of these form one strongly connected component. For these four vertices, any pair I choose is connected. Similarly, for these 4 vertices, any pair I choose is connected. Yeah, and that should somehow tell you how to do things.
Both of them must be parts of cycles. Both of them.
Right, something like that. So, if there is a notion of strongly connected, there should be a notion of weakly connected. Not daily, weakly connected. Huh? Okay, sorry. It's weakly connected. So, what do you think is a weakly connected graph? Yes.
So as undirected they are connected.
No, no, not as undirected they are connected. The following is
There has to exist a path. There is a path from U to V or
there is a path from
U to V or V to U.
or V to U and or V to U. The following graph, is it weakly connected? Yes? B और D के बीच में कितने पाथ मिल रहे हैं आपको? Is there a path from B to D? No. Is there a path from D to B? No. Is it weakly connected? No. This is not a weakly connected graph. Right? So, why am I showing you this example? It's not sufficient to say कि आपने edges directions ignore कर दीजिए. अगर graph connected है तो it becomes weakly connected. So, this is a graph such that if I were to ignore the directions, it is a connected graph, but it's not a weakly connected graph. So, what's the right definition of weakly connected? A graph is weakly connected if for every pair of vertices u comma v, there is a path from u to v or a path from v to u or both. If both the paths are there, it is okay, and this should be true for every pair of vertices, right? हर एक pair of vertices के लिए ये true होना चाहिए. तो तब हम उस ग्राफ को वीकली कनेक्टेड कहेंगे. Right? Good. So, I told you what a strongly connected graph is and what a weakly connected graph is. So, a natural question is, given a graph, is it strongly connected? Huh? Given a graph G, is G strongly connected? So, what are you saying? We are doing a DFS starting from here. So, we have to check. So, strongly connected means that we have to check that from between every pair of vertices, every ordered pair of vertices, there is a path. So, from U to V there should be a path, and from V to U there should be a path. So, one solution that is being suggested is that you take one vertex, do a DFS from here. It should visit all vertices, right? Then take another vertex and do a DFS from there. It should also visit all vertices. Take a third vertex and do a DFS from there. It should also visit all vertices. So, do this DFS how many times? N times from every vertex. If each of those DFSs visit all the vertices, then the graph is strongly connected. Yes? Is that clear? Is this argument clear? If all of these DFSs visit each and every vertex, then the graph is strongly connected. Perfectly okay, except how much time does it take? Order mn time. Yeah? That is too much for us. We want to do it in linear time. Right? So, we want to do it in order m plus m time. So, the question is how will we do that? ठीक है, तो थोड़ा दिमाग लगाना पड़ेगा. So, try to think about this and think in terms of the procedure we used for 2H connectivity, right. We will borrow ideas from there, right. In 2H connectivity, what did we require? We required that for every subtree there should be an edge, back edge going out of that subtree, so to say, going to a ancestor of the root. Here also we will require something similar. That is the hint. Okay. So, you will have to see what that is, and we will discuss it in more detail in the next class. Okay.